Hi, I'm Gray, and my project was on applying gradient domain image processing to high dynamic range images. So why did I think this might be a good idea? Well, the first one was that I wanted to play more with gradient domain image processing after assignment 2. But there are some decent theoretical reasons to do this. The first one is that the human visual system is much more sensitive to edges between objects than they are with absolute brightness. For example, on the right, I have a pretty common optical illusion where the two dots are actually the same absolute brightness, but because of their surroundings, we perceive the right dot to be significantly darker than the left dot. And this can be exploited to produce better tone-mapped HDR images on limited dynamic range displays. Another advantage is related to the fact that our noise model for cameras involves Poisson noise, which, as you probably know, is not very Gaussian. However, if you subtract two Poisson variables, for example, taking the discrete derivative of them, you get a Skellum distribution, which is much closer to Gaussian for a wide range of inputs. And finally, I found an interesting paper on HDR tone mapping using gradient domain processing that I wanted to play with. The first thing that I tried was to merge a stack of LDR images into a single HDR image directly in the gradient domain. This should be possible because taking the gradient of an image is a linear operation, which means that if we add up the gradients of the images and then integrate, it should be the same as if we had just added up the images originally. Additionally, this would allow a lot of interesting tricks involving playing with the direction of the gradient versus the magnitude of the gradient in each image, because the directions should all be the same up to clipping, even though the magnitudes will differ. Unfortunately, as you can probably see on the right, this doesn't work very well in practice. The reason for this poor showing is due to a few things. First, because we're taking the discrete derivative by taking adjacent pixels and subtracting them, every clipped pixel actually affects both itself and the pixel next to it, increasing the amount of lost pixels during the reconstruction. This is especially bad because in the gradient domain, only a few pixels are actually important due to the sparsity of the gradients. And unfortunately, the most important pixels, the ones that have a high difference between them, are exactly the pixels that are likely to be clipped on one side or the other. Another issue related to this is that there are actually some pixels where the gradient is so high that no single LDR image can actually measure it. If, for example, on one side of the edge you have a extremely bright spot, and on the other side you have an extremely dark wall, no single image will actually properly expose both sides, meaning that we don't have a good measure of the gradient anywhere in our input. Moving on from that failure, I decided to try re-implementing a paper on tone mapping an HDR image in the gradient domain. And again, this is basically to exploit our human perceptual bias for local changes in contrast being more important than absolute brightness. And the key insight here is that the direction of the gradient plays a much greater role in the final image than the absolute magnitude of the gradient. And the high-level idea is that if we attenuate the large gradients much more strongly than the small gradients, as long as they're all facing the same direction and have the same ordering of relative magnitudes, the output image will still make sense to us. One interesting challenge with this technique is that there's actually two different kinds of large gradients that we need to attenuate. The first obvious one is a very sharp line between a bright object and a dim object. In this case, the gradient domain will have a super bright pixel and we can attenuate it appropriately. However, there's a lot of cases where the edge between a bright object and a dim object is actually spread out over several pixels, but we still need to attenuate it. Each of the individual gradients in this edge are relatively small, but altogether they add to a very large change in brightness that causes problems. We solve this by actually doing gradient domain operations over a pyramid of images, starting with a very small image where each pixel is a large change in space, and then applying the results upwards as we get to bigger and bigger images. In this way, we can detect both large spatial gradients and small spatial gradients and attenuate both of them appropriately. Moving on to results. On the left, you can see a typical result of the homework 2 tone mapping process in the primal domain. And on the right, you can see my results using the gradient domain image processing. You can see that while the colors are a mess, and we'll talk about that, it's actually a lot easier to see detail in both the right side of the image and the left side of the image because of the much more aggressive equalization of brightness between the two sides. Here's another example of tone mapping comparing the standard intensity tone mapping to the gradient domain tone mapping. You can see that in the intensity domain, all of the colors actually make sense, but on the other hand, you can't see very much of the background because the sky outside is simply too bright. While on the right, everything is still in detail, even if it looks more like a dreamscape than a real image. So what causes the strange behavior that you saw in these past few images? Well, the basic problem is that the attenuation was both computed on and applied in to the luminance channel of the images. And so we need a way to get from that to the full color images. And the paper proposes a system where you basically apply the luminance of the input and the luminance of the output as a scaling factor on each of the color channels, with a power term to make the colors not totally wash out. Unfortunately, that produces what you saw, which is very garish images with weird colors, no matter what parameters I tried. There are other ways to do this, such as applying the scaling and then integrating each of the color channels individually, but those caused even bigger issues that you can see in my paper. So we need a better way of applying this to full color images. And another issue that's actually sort of fundamental to this is that after scaling the gradients, it's actually not very integrable because we've added a lot of curl. Because the larger gradients that normally counteracted a bunch of small gradients are now smaller, and so they no longer actually counteract them properly. And so that meant that integration took a long time and still resulted in some weird artifacts that you can see if you look at the images closely.